Okay, so now what we want to prove is again a graph has unique edge weights. Now, if we have a graph, we could have cycles in it, right? So only tree does not have cycle in it. A graph can have cycles. So for example, there could be a cycle like E, F, G. Is that clear? So um, now since the graph has again unique edge weights, every cycle has to have some edge that is of the largest weight among the edges in that cycle. So for example, in this cycle, 11 is the largest edge weight in this cycle. So like that, every cycle in this graph has some edge that has the largest edge weight. So the theorem or the property is the largest edge weight, okay, of any cycle in a graph of unique edge weights. Okay, so if a graph has unique edge weights like this, where no two edges have the same weight, then for any cycle in the graph, the largest edge weight, uh, the edge with the largest weight in that graph in the cycle, the edge with the largest weight in the cycle cannot be part of any minimal spanning tree. Is that clear? So that's the property. So like for example, you have a cycle here from EFG. So the edge weight, which is largest weight, is 11. So this edge from F to G cannot be part of any minimal spanning tree of that graph. So how we prove that? Again, we'll prove by contradiction. Let there be a hypothetical minimal spanning tree that has this F and G as part of the minimal spanning tree. Now we already proved a property. If you have a minimal spanning tree, then every edge in the minimal spanning tree is part of an ij cut, which means if I remove that edge fg like this, I'm going to divide the vertices into two components like this, okay, and you have some edges crossing the cut, right? So fg has to be the minimal weight edge in that cut, right? But fg is also part of a cycle. As per our assumption, there is an edge that is the largest weight edge in a cycle, but it is part of the minimal spanning tree, right? That's our assumption. So which means what? If there's a cycle involving f and g, a cycle means there is an alternate path between any two vertices. There's not just one path between any two vertices. In a cycle, you have alternate paths. So which means from F to G you have this direct edge. There's an alternate path from F to G through E like this, F, E, G. Now one of the edges in that alternate path should cross the cut, right? Should cross this cut, because FG is the edge. You remove that edge from the spanning tree, you create the cut, okay, on the two components like this. So the alternate path basically connects F to G. So one of the edges in the alternate path should cross the cut, and the weight of that edge that crosses the cut should be less than what? The weight of this edge FG, because that's the largest weight edge in the cycle, right? So which means we could remove FG from that uh, minimal spanning tree and connect the two components with this edge EG that happens to be the that happens to have what? Weight less than the weight of FG, which is the largest edge weight in the cycle, right? So which means this tree is not a minimal spanning tree to start with, because you are going to remove this edge FG and going to add an edge of weight less than this edge FG. So we are telling that the weight of this tree could be reduced even further, right? Strictly reduced, because all edges have unique edge weights. So which means this is not a minimal spanning tree to start with. Okay, so that contradicts our assumption, because our assumption is you have a minimal spanning tree and one of the edges in the minimal spanning tree is the largest edge weight in the cycle. So which means what? Since we proved that's a contradiction, if you have a graph with unique edge weights, then uh, the edge that has the largest edge weight in any cycle. Okay, so you have several cycles, right? In each such cycles, the edge with the largest weight cannot be part of the minimal spanning tree. Okay, stop here.